The person you see here is holding a bowling ball at rest above his head. And that person is doing no work. The symbol we use for work is capital W. So we say work equals 0 in this case. Now to be clear, this person is definitely exerting a force if they keep that bowling ball at rest. The bowling ball has some weight, and the person applies an upward force that's no bigger, no less, but exactly equal to the weight of the bowling ball. But we can't confuse work with force. Work does not equal force. They're two different quantities. Force, as we know, is any push or pull measured in newtons and really comes in four varieties: gravity, electromagnetic, strong nuclear force, and weak nuclear force. Work, on the other hand, well, our definition differs from the everyday language. In everyday language, we might describe work as something you should get paid for or something that requires effort. And I think of effort as being like force. Now, work does have something to do with effort. Work is a product of two things. One, force. So I can see why some people might confuse work with force, because work is produced when a force corresponds to some displacement, meaning an object has to move for work to be done on it. Now, when we say product, we mean that in a mathematical sense. So we can say work equals force multiplied by distance. Now, wait a minute. How do we write that? Do we say dot? Or do we say x? Or does that just mean the same thing? I remember back in elementary school, this must have been around 3rd grade or so, we had our times tables that we had to memorize. And my teacher posted several note cards in the classroom. 1, 2, 3, etc. 1, 2, 3. And that card said 1 by 1, and this said 2 by 1. And this said 1 by 2 and 2 by 2. And this said 2 by 3, and so on. And if you went to the back of the room and lifted up the note card, underneath revealed the answer 6. And underneath this one revealed the answer 4. And we had to memorize our times tables. And I quickly learned that putting an x in between two numbers means you're multiplying them together. And then I got to the next grade level, and I found that sometimes you could put a dot in between two symbols, and that meant multiply. In fact, I think it was in 6th grade that I first learned you can multiply letters of the alphabet together. And I was told you could multiply A times B. When I got to junior high school, I was told to multiply x times x. So I wrote it like that. And my teacher was a little disappointed. He said, this is probably a case where you'd want to use the dot. And then the very next year, I had to multiply x times y. And I realized, I'm not going to fall for this one. I'm not going to write it as x, xy. I know better. I'm going to write a dot. And my teacher said, no, you don't need to do that. If you just put xy, that's implied that you're multiplying the two of them together. So, back to my question, how do we define work? Do we say work equals F times D? Do we say work equals F times D? Or do we just say work equals FD? Well, it turns out you already know that displacement, oh, and I guess instead of D, it would be just as well to write delta x, whatever symbol we want to use for displacement. Anyway, it turns out that displacement is a vector quantity, and force, as we know, is a vector quantity. Well, this symbol actually means a special type of multiplying called a cross product. And a cross product of any two vectors always produces a new vector. But I'll tell you something, work is a scalar quantity. So this is not the way we express the equation for work. When we take this type of product, known as a, you guessed it, dot product, a dot product always produces a scalar quantity. And because we're multiplying vectors together, this expression doesn't cut it, because just writing two quantities next to each other is a way of taking a scalar product. So, indeed, the way we define work in terms of an equation is W equals F dot delta X. Or, if something's moving along the y-axis, we might say F dot delta Y. In fact, in general, something can displace at an angle. So it has a displacement component along the y-axis and a component of displacement along the x-axis. So maybe we name displacements as delta S. So there we have it. We will formally define work in a mathematical sense as the vector dot product of force and displacement. It would be incorrect to put that symbol above the W because work is not a vector quantity. In fact, there's another definition of work. Work equals a change in energy. There's a lot of different types of energy. There's energy of motion that we call kinetic energy. Well, it takes work to make something move faster and faster. It takes work to make something increase or decrease its kinetic energy. Energy at rest is known as potential energy. You can give something potential energy perhaps by compressing a spring, and if something's spring-loaded, it's just waiting to be released. Well, it takes work to compress the spring in the first place. What other forms of energy? There's a lot. We can talk about thermal energy. Take your hands, clap them together, and start rubbing. Your hands will quickly heat up, and you'll generate some thermal energy in that case. And that takes some amount of work. In fact, the displacement comes from the motion of your hands, and the force comes from the force of friction when warming your hands. So anytime that a force couples with a displacement, then there's almost guaranteed to be a change in energy. Well, because work is a change in energy, work should be the same type of quantity as energy. In other words, both of them are scalar. Remember the difference between scalars and vectors. If it makes sense to state a direction at the end, then it's a vector quantity. But if you give a number and at the end of that measurement you don't have to say any units, then it's a scalar quantity. Oh, take a look at a box of food in your pantry, whether this is a box of cereal or this is a box of macaroni and cheese, whatever it is, more than likely somewhere on the side is a nutrition label. And we're told the amount of energy in the form of calories. I've yet to find a food label that says a whole box of macaroni and cheese provides 300 calories at an angle of 30 degrees, or an entire container of chocolate chip cookies gives you 900 calories southwest. Of course not. It doesn't make sense to give a direction when describing energy, and therefore it doesn't make sense to give a direction when describing work. Work is a scalar quantity defined mathematically as work equals the vector dot product of force and displacement, or conceptually, work always produces some sort of change in energy. In the next lesson, we'll get into more detail about how you accomplish taking a vector dot product mathematically and provide some example problems. Thanks for watching.